So here we have a fairly simple example where we have this circuit with a 10-volt source and a 1 voltage source and a 1 amp current source. They're asking us to find the Thevenin equivalent circuit for this circuit between terminals A and B. So that means we should be able to replace everything to the left of those terminals A and B with a single voltage source in series with a single resistor. So let's see how we would go about this. So the first thing we want to do is to calculate the Thevenin resistance, and so that'll be RTH, and that'll be looking back into our circuit here. So we recall when we do that, we open circuit all current sources. So this current source here would be as if it's not even there, so we'll open circuit that. So that's gone. And then voltage sources we short circuit when we're calculating the resistance. So in this case, we will short circuit this. So now if we come back, we see that we have 5 and 5 in parallel. So 5 in parallel with 5, that'll be 5 times 5 over 5 plus 5. That'll be 2.5 ohms. So then we can replace both those resistors with just one resistor of 5 ohms. So that'll be like this is all gone now. And then left with that just being 2.5. So now we see that we have the 7.5 in series with the 2.5. So then that means 7.5 plus 2.5. So they're in series, you just add them together, and that's 10 ohms. So that means you can replace both of those resistors with just one resistor. So we'll do that. So that's gone. And so if we come back, we'll just have one resistor of 10 ohms. And so finally, we see that we have a 10 in parallel with a 10. So when we combine these two, that'll be our Thevenin resistance. So let's go ahead and write that then. So now our RT is going to be equal to 10 in parallel with 10. So that'll be 10 times 10 over 10 plus 10. And when we work that out, it comes out to 5 ohms. So now we have our Thevenin resistance. Now all we need to do is figure out the voltage, which let's mark this off first. So we're done with that. So let's reset our circuit. So we can do that and look at that. So here's our original circuit. So now we need to find the open circuit voltage here between A and B. And so that would be the same as if you put an ideal voltmeter there and measured the voltage. What would you read? And so when we have that, that'll be our Thevenin voltage, and we have our Thevenin resistance. So we're just about there. So the first thing we want to look at is we want to do a little simplification. And we see that we have this current source and this resistor in parallel. So that means we can do a source transformation and replace that with a voltage source in series with the resistor. So let's look at doing that. So recall, or let's go ahead and mark, we're replacing what's between those two nodes there in red. So when we redraw this, we'll start out with our original voltage source. So this is our 10 volts, and that comes up, and then we still have this 5 ohm resistor, and that's get my pen right. That's 5, and so here's our node that we were talking about that we're replacing. We still have this 5 ohm going down, so that stays the same. So now starting with this node, we're going to replace this with a resistor in series with a voltage source. Now the positive sign goes on the same side as the direction of the original current source. The resistance stays the same, so that's 7.5. The voltage value is the product of the two, so that's 7.5 times 1, so that's also 7.5. And so there's the other node that we marked in red above. So that's what we replaced in between those two red nodes. So from here we come down with the same 10 ohm resistor. That doesn't change. And we come back to our original terminals. So as far as the terminals A and B are concerned, nothing would look any different from those terminals between the top circuit and the lower circuit. They should be electrically equivalent. But in this form, we have it in a form that is easier to analyze. So we can now do some voltage loop analysis. So we'll define some currents, some mesh currents. So the first mesh current is here. We'll call this I1. And then we'll define another mesh current here. We'll call this I2. And so now we should be able to write the loop equations. So we'll start with I1, the ones contributing from the loop from I1. So we'll do that in green here. And we see that we have a voltage source and two resistors. So whatever the voltage drop across the two resistors is should equal to the voltage source. That's all the sources in the circuit. So we can write that then as 10 volts has got to equal to, now if we look at the first resistor, which is here, we see it only has a current contribution from I1. So we will say 5, let me do that in blue, 5 times I1. And next we will have the other 5 ohm resistor, which is here. And so when we write that, it has both currents passing through it. So we've got the I1, so again, that's going to be plus 5I1. Then we've got I2 going through that same resistor, but it's going the opposite direction. So it's working against us, so that'll be minus 5I2. Oops. I2. And so then that's everything in that loop. We've accounted for everything in the loop. So now we want to move to the second loop with the mesh current I2. Same type of thing there. So we have a voltage source. This time we see that it's pushing in the opposite direction of our current flow, so then it'll be a negative 7.5. So it's working against our current, at least the way we've shown it. And so that's got to equal to the voltage drops across all the resistors. So the first one we can do is the 5 that's already highlighted in purple. And we know that that's going to be 5 times I2. But it's also I1 goes through that resistor in the opposite direction. So it'll be minus 5 times I1. Okay. So then we also have this 7.5 resistor. The only one that goes through that is I2. So then that'll be a plus 7.5 I2. And then finally, we have this 10 ohm resistor here. And again, the only thing that goes through that is I2. So then that'll be plus 10 times I2. So now we can combine like terms and rewrite this a little bit. So let's draw a line here and do that. And when we do, we should have 10 times I1 minus 5 times I2, and that should all be equal to 10. So that's the first equation, or the green equation above, rewritten. And then below that, we should have minus 5I1, and we should have plus 22.5 I2, and that should equal to a negative 7.5. So now we have two equations, two unknowns. There's several different ways to solve that. You can use algebraic substitution. You can use linear algebra with matrices analysis, whichever of those you want to do. But when the one we're interested in though is I2, because if we have I2, then we can figure what the voltage is across these terminals. So when we solve this, we come up with I2 then is equal to a negative 1/8 of an amp. Negative 1/8 of an amp. So then that means that our open circuit voltage, OC, which that's the voltage across here, right? It's what we've been looking for, this VOC. What that will equal then to is just the current, using Ohm's law, it's just voltage, it's just current times resistance. So in this case, the current is I2, and the resistance is 10. So then that'll be minus 10 over 8, right? And so we can reduce that to be minus 5/4 of a volt. So now we have our open circuit voltage, and we have our Thevenin resistance. So we can now draw our new circuit. So we'll have this voltage source and a series resistor, which is the way all Thevenin equivalents look. This is the standard form. This resistor will be our Thevenin resistance, so it'll be our 5 ohms. And this voltage source, since it's negative, we'll have a negative sign up top, and it'll be 1.25, or 5/4, same thing, volts. So this is the Thevenin equivalent circuit for our original circuit up here. So as far as A and B terminals are concerned, these two circuits are equal to the left as far as what we would see if we probed it with a meter, not knowing anything else.